Hello everyone to this new video in our series about generative AI. In this video we will be starting fine-tuning. So my plans is to divide this video into two parts. So in this first part I will be introducing the fine-tuning and going through the answers which we will be using to do the fine-tuning. And then in the second video I will show you how you can generate data from your custom data. So I will be using the same PDF file which we used for the RAG, so namely this direction finding paper, and from that paper I will extract some data which I will use in the fine tuning. Let's start first by the general idea of the fine tuning. So in fine tuning you will have a base neural network as the one shown here in this slide. So this is a small neural network just for the purposes of demonstration. So the first kind of the fine tuning is that you download these pre-trained weights from somewhere and then you use your data to fine-tune all the weights. So basically here we have two layers, so you fine-tune this first layer and the second layer. So really all the parameters. This will become very difficult for us to do it locally for LLMs, since those contains like billions of parameters and not only tens of parameters like shown in this figure. So when you have billions of parameters, tuning all the parameters will require really a huge cluster, and that can be done only by large companies. So the second kind of fine tuning is adding new parameters. In this approach, we download this pre-trained model and we fix all these weights. So we will not tune those. We'll use them as a backbone, and then we, for example, add a new layer here. Let's say 4 neurons, and let's assume now there are connections from all the neurons in this layer to the one in the final layer here, and we fine tune now this layer here, the new added layer. And of course you can add as much layer as you want depending on your data and your purpose of your fine tuning. Now this can be simpler than the previous one. So if you have a huge neural network which have billions of parameters, you can add few layers with few millions of parameters and you can tune those. The drawback of this approach is that you are adding new layers, which means you are adding new computational cost and new memory to your LLM. Then in the third approach, we're tuning some of the parameters of the neural network. So basically we download this network and we fix some of the layers. Let's say we fix this first layer and then we tune only the second layer, for example. And that's also can be done. And then here you will have multiple questions, like for example, which layers should you keep? Which layer would you like to tune? And that could also have some drawbacks. The approach which we will be using in this series is the LoRA, or what's called a low-rank adaptation. So I will demonstrate now the low-rank adaptation for one layer. So let's say that, for example, we want to tune the last layer from the previous figure, which has like 4 neurons as input and 3 as output. So basically the weights can be represented as a matrix W2, which is 4 by 3. So thus like 12 parameters. And let's see how we can approximate 4 by 3 matrix with rank 1 matrix. The rank 1 approximation of a 4 by 3 matrix can be seen as a multiplication of a column vector of 4 elements, like this vector here A, with a vector B which contains 3 columns but only 1 row. This outer product will produce a 4 times 3 matrix, where this components here is a multiplication of the corresponding columns from column A with row B. So this one will be A1 times B1. So then here we will have A1 by B2, and then here A1 by B3, and so on. And here the last row, you are multiplying this A4 with the whole row here. So you have A4 times B1, then A4 times B2, and then A4 times B3, and so on. So this is a rank 1 approximation. You can see now in this approximation, instead of having a full matrix, which is like 12 parameter, we will have only 4 parameter plus 3. So that means like 7 parameters, which is less than these 12 parameters here. Of course, we can have a rank 2 approximation for a matrix, and in this case, we will have like 2 column vectors. So 1, 2 here multiplied by 2 row vectors, and so on. So we can have like rank 3, 4, and so on. And you can see that now the number of parameters would be the sum of the parameters from the column vectors plus the ones from the row vectors. And so now imagine that we want to have a rank 10 approximation of a matrix which is 100 by 100. So this matrix will contain 10,000 parameters, so 10k parameters. If we want to have rank 10 approximation, then we will have like 10 column vectors. So that would be here we will have like from 1 till 10. So that means we are having 10 times 100, so those are 1000 parameters, and multiplied by 10 row, which is also like 1000 parameters. So in total, we will have like 2000 parameters, which is 2k, and that's much less than this 10k here. So that's how the LoRa works. And let's now go to the ansloth and see how we can use it to do this low rank adaptation for fine tuning. So this is the anslas.ai website. We can click here to go to the GitHub repository, and in this repository you can see some information about Anslas and how can you use it. You can see here like Finetune for free, and it's showing us all the notebooks which are beginner friendly. And you can see here these notebooks are divided based on the model. So we have this Llama 3.2 and then V4, Llama 3.2 with Vision 3.1 and so on. Yeah. I usually prefer to use the Llama 3.2, namely because it's smaller and it was designed like from the beginning to be used for low-end devices. So let's click here on this start for free. This will take us to this Colab, and of course you can go through the Colab yourself, and you can see here first you have this installation. You can run it cell by cell. There are like few cells here. Then this will run on Google hardware, and that's okay if you don't have like local hardware and you want to use really Google hardware for that. For me, I would like to use my own hardware. So what I did is now I copy pasted all these cells in one notebook in VS Code. So let me now open VS Code. So this is the repository of this series. We had code for now in video 3 and video 7, and now this is video 8, and I already prepared the code for this video. So the first part, which is really just the copy paste from the Anslas Colab, is this file here. So let me go quickly now through this code here. I have like here some comments which I hope will be helpful for installation for you and for reading. And I am using Windows, so there are some parts which are like really special for Windows, which you don't need if you are using Linux, namely this installation here, Triton. So this is really required by Anslas, and to install it in Windows, you can really use this command here. So we are downloading the binaries from this website and installing them locally. And of course, we need Torch to be installed. If you don't know how to do it and you want to install another version than the one that I have, for me, I have like Coda 12.4. That's why I'm using this command here. If you have other versions of Coda and so on, so simply you go to Google and search for pip install PyTorch, for example, and then you can see here the first link from pytorch.org. You click on that, and yeah, here you can choose what version of PyTorch you want to use, what's your operating system. I'm using pip, for example, here, and then the Coda version. So for 12.4, I need to select here, and then you get the command here. So that's all. When you installed Torch, you can install now Anslas using this command here, and then Triton as I explained here. Then there are these two links here for reading. If you have some time, really go through these two tutorials. They are very good. So now let's go through the code. So the first cell here is just really to test the installation of PyTorch. So I'm importing Torch and I'm checking if Coda is available. Let me run this by pressing Ctrl Enter. So you can see the output is true. So we have Coda. Now the second part is actually contain all the imports which we need from Anslas and from the Hugging Face. There is this first definitions here, so the links of our input and the types of the data, so which kind of float we want to use, and if we want to do a quantization for 4 bits. So this is a way to make our LLM smaller using quantization. So instead of having 4 bytes for the float, you could have 2 bytes. That means you already divided the size of your network by 2, and then you can have also 1 byte or even 4 bits. That's a really huge optimization. So for now, I will be keeping everything here to none, and I will put 4-bit to true, so that will make it very small and make the download of the pre-trained weights faster. So here's the part where we are now downloading the pre-trained weights, as you can see here. So we are using this fast language model class from Anslas, and you can see this function from pre-trained. So we are giving the name of the model which we want to download. And yeah, as you can see here, so this is Anslas Llama 3.1 billion parameter instruct. So this is really coming from Hugging Face. So let me go to Hugging Face. So as you can see here, so if you went to the model, and then you can search for this model, we press enter. So now you get the information of this model here. That's the model which we are using. So this function will return for us the model and the tokenizer. Then we are using this function get. So PEF means parameter efficient fine tuning. And as you can see here, we are defining our LoRA. So we are saying that we want to have a rank 16 model here. That means for each layers, for example, now if our layers are like 1000 by 1000, instead of tuning 1 million parameter, we will be tuning only 1000 times 16 times 2, so 32,000 parameters. And then we are choosing the layers which we want to tune here. So this is as normal fine tuning, and then some parameters about the dropouts and bias and so on. So this function will update our model and prepare this new low rank parameters for fine tuning. So let's run now this cell. So you can see here the output now it's saying that Anslas will batch your computer to enable 2x faster. Don't worry, it's not batching the computer, it's batching really the model. So a few seconds, it's done. Then we can move now to the third step, which is preparing the data. And for that, now we are using this get chat template function from Anslas, and it requires the tokenizer and the name of the chat template. So we are using Llama 3.2 that will update our tokenizer. And then we have a small function here for formatting the prompts. So this function will take one input example from the data. So this example will contain a dictionary. As you can see here, this dictionary will have some data under conversations here. And this function will take this data and will apply the chat template to it and return a dictionary which contains a key called text, and the value corresponding to this key is the produced template. And then here we are loading the dataset. So let me run now this cell. Let's check the dataset. So you can see that the dataset has like conversations and source and score. So let's see under conversations. Under conversation, you can see that we have a list, and this list is contain so another list inside it where you can see we have like a from human and then the value explain what Boolean operators are and so on. Let's see only one element now from this list. So you can see it's really a list of two dictionaries. So this is the first dictionary till here, which contain one message. So a human asking a question, and then the GPT is answering this question. Then the second cell here, we will change the format of this dataset. So first step is to standardize this chat GPT. Let me run this command now here, just to see the output now. And now let's look for the first element of the conversations in this dataset. You can see now what have been changed. So now instead of having the keys from and value, we have the role and the content. And this first message, now we have the role user. So the user is asking a question and then the assistant is answering that question. Now let's apply our formatting prompt function here. So let's run it. And now let's check the first element of the conversations. So it's not changed, but now I think we have text, as you can see here. So let's take the first element of text. And you can see here that the chat template has been applied to this text. Yeah, so we start here by begin of the text, then start of the header. We have like a system here. Then you can see at some point we have in the header, we have a user. And then after that, we have two new lines and then explain what Boolean operator are. So this is the question. And then we will have again. So now this is all the question. Yeah, I mean, it's a very long question. And then here, after the end of the question, we have the end of token ID. Then we start a new header where we have the assistant and then the answer for this question and so on. So now we really applied now this cell here. So our data is ready for training. I really want a little bit of details in this data because this is really the step which we need to do every time we want to train an LLM using a new PDF or a new dataset. So you really need to understand this very well, while the other parts will not change that much really. So the next cell here, we are initializing the trainer. So there are some important parameters here which you may like to play with depending on your data. So for example here, how many steps you want to run, the learning rate, and so on. So these parameters could affect how much your network is learning your new data. So for example, if you use a very huge number of steps, let's say 1,000 or so, that means your loss will drop very much. You will be really near zero on the training data. That may also cause that the network is forgetting older data. So really here, the higher means the more you are fitting your new data. So be careful in choosing this parameter. Also be careful when choosing the learning rates and the decay strategy. I will now keep these defaults here, which I got from this notebook, but be careful that some of the parameters here can cause your training to overfit your data. And now here we are setting the trainer to train only on the responses. Let me run this cell now. Just press Control Enter. So it's finished now. So let's go to the next cell. In the next cell, we are just verifying the tokenizer. So let me run this cell. And then let's move to the next cell, which is really doing the training. As you can see, it's just trainer.train. Let me run this cell. So as you can see, it will take some time for 60 steps, but don't worry, I will fast forward. So training is finished, as you can see here. So let me scroll up here. You can see we started by a loss, which is by 1, and now got lower, like 0.7 at some points. And the output result is saved here inside this folder called output. So I forgot to mention that here. So inside this training, so when we prepared the trainer inside this training arguments, so where we have the number of steps and so on, we have this output folder and we put it to be outputs. So the trainer saved the output here inside this folder. There's also this folder here called Anslas compiled cache. So this folder is also used by Anslas. So all the code here is generated automatically by Anslas. So I will not touch it. Yeah, the other two folders here which I have. So this is, as the name says, I will be using it to save our own CSV data, which we will use later for tuning in the next part. And here I will put the final models. So after training, I will save the models here. So that's about the structure of the folders which you see here. And then about the training parameters, there is another two parameters here which I forgot to mention something about, which are the batch size and the gradient accumulation step. So this is basically how big our batch is. So we are saying 8. So that means the trainer will take 8 samples from our dataset and use it for the training each time. So you can make this larger if you have larger memory or smaller if you have a smaller memory, so depending on your GPU memory. And this parameter is basically how many steps we want to do before we update our weights. So here I kept the default, as you can see. So now we already run the trainer.train and we finished training our network. We can really directly now use it for inference. So we're using Llama 3.2, and as you can see here, so again we are getting the chat template, and then we are using it for inference. So we are saying put the model for inference, and then we can ask a question from this dataset. So here is about the Fibonacci sequences. The question is, let me run this code here. So as you can see, we really got here the answer. I will not go through the answer and how much is correct and the comparison of the network before and after training. That I will do in the next part when we train our model for our own data, namely for direction finding. And now let's go to the part about saving the model. In this notebook, there are multiple options. So for example, we can use model.save pre-trained, and that will save the model here, as you can see, and the tokenizer to a folder called LoRA model. Let me run this. You can see here now we have this folder called LoRA model where we have the adapter configuration. So this is for the LoRA, and here we have the tokenizer configuration, and here we have the adapter model. So this is a safe tensor, as you can see. Let me open this in the Explorer. So you can see now that this safe tensor is really small, only 44 megabytes, and that's because we only use the small rank adaptation. So I think the base model for 1 billion parameters is around a gigabyte. However, here we have like only few megas. So really the result saved here is only the new parameter, but not the original one. So basically to do inference, you still need the pre-trained parameters. So that's how the inference works. So it would take the pre-trained parameters and then the fine-tuned one, so the LoRa one, and then we'll sum those. So I forgot to mention this. And then after summing those, you get your really fine-tuned network, which can be used for inference. And since we sum the original parameters to the LoRa adapted ones, that means the number of parameters did not change. So if we have like 1 billion parameters before training, so after doing this summation, we'll end up also with 1 billion parameter. And that means the same computational cost. And that's also another advantage of this LoRa models. So now we have saved the fine-tuned LoRa model. Then anytime we can load the original model, so the pre-trained data and the fine-tuned one, and merge them and do the inference. And that's shown in this snippet here. So this is here is set to false. That's from the original Colab, but you can see it now. It's just like really loading. So if you want to do inference, even after restarting your computer, you can just load those from the folder called LoRa model, and the fast language model will look there and will know also where to get the pre-trained model and merge it with this LoRa and prepare everything for inference for you. So that's all for this video. In the next video, I will show how we can use our own data to fine-tune the Llama 3.2 instruct. This would be these two files here. And I will also show how we can merge these models and save them in one gguf file. So the UF is coming from universal format, and that can be used also in OLLAMA or using another package called llama.cpp to do inference using this new fine-tuned model. So see you in the next video. Bye.